Hi, my name's Andrew McLaren. I'm going to be going over the difference between weight and mass. These are two terms that are commonly used in everyday English interchangeably, but they actually mean slightly different things in science. So if you're on the moon versus Earth, you may have heard that you would look like you're a different weight on a scale, like your weight that when you stand on it, it might measure out something different. So we're going to talk about that as well as what would happen if you were in an elevator standing on the scale. So in that situation, there is a change in gravity, which is going to cause a change in your acceleration, which in effect will also change the measured weight. There is still the same mass between these two situations. Like you haven't lost any stuff. You're still like the same density, all that is pretty basically the same. There might be a difference in the air resistance, but we're going to assume that air resistance is very small, and not really affecting how much you're being weighed down by, especially when you're standing still. It would be negligible or absolutely zero if you're standing still. So the formula that you're going to want to be referring to here is your force is equal to mass times acceleration, or force of gravity is related to the mass times the acceleration of gravity. And in this situation, these values, some of them stay the same, some of them will be different. So in Earth's gravity, that force is going to be related to whatever mass we're talking about times negative 9.8 meters per second squared. It should be pulling you down, so I'm going to put the negative value in for that. But this is going to be your mass pulling you down, and this is the force of gravity. So in other words, we have mass here, and then this is kind of like your weight. It's going to be something measured in newtons versus something that's measured in kilograms. And then if we're talking about our force of gravity on the moon, you've got that force of gravity on the moon versus the Earth. Slightly different values because our acceleration is different. We do still have the same mass, but here on the moon, you're going to be accelerating at negative 1.67 meters per second squared. So like the moon, things kind of fall slower. You may have heard that or even seen some videos with that. Here your mass, if we're talking about like a person, that mass is staying the same. But the amount of force that's pulling downward, that weight, is now going to be different. In reality, this is somewhat true. We're going to be talking about your weight essentially being your force of gravity, but in a more accurate sense, it's more like your normal force. So if you're standing on some scale, there's some scale here. It doesn't really know how much mass you have directly. It knows how much force is being pushed down on it. So scales on Earth are kind of like zeroed out for Earth. So they know, oh, if I'm feeling this much force, that corresponds to a certain amount of mass. So if you have your gravity pulling you down a certain amount, that's like the force of gravity of you downward, and then there's a force normal, which is how much the scale is kind of pushing up. If we are talking about standing still, those two values should be equal and opposite to each other. So this force normal up should be equal to that force of gravity. So let's say that my mass is 100 kilograms. I'm kind of a big guy, so that actually is accurate for me. So in this situation, the force of gravity standing on Earth would be 100 kilograms times that negative 9.8 meters per second squared. And I am being pulled down at 98 newtons. And therefore the force normal, if it's equal and opposite, would be a positive 98 newtons. When that scale feels on it that compression, like it's that force normal for it to push up, we need to be pushing down on it that amount. It's going to look at that number and be like, oh, that's 100 kilograms. And so the scale, if you were to take it to the moon, you would get a slightly different readout than 100 kilograms. So like you would look at this force of gravity and it's going to be 100 kilograms, but now at this negative 1.67 meters per second squared. I think I missed a place value. This would be 980. And then this is going to be 167 newtons downward if we're talking about the moon versus the Earth. And therefore, in that situation, if we're not accelerating upward or downward, the force normal is going to be a positive 167 compared to that 980 newtons. And so it's going to look at that and be like, oh, that's not 100 kilograms. It's going to give you a readout that's smaller. We could, if we wanted to figure out the exact value, we could do the 9.8 here and be like, oh, 9.8 times what would give me 167. So we could do that. Let's say that we're saying you got 167 newtons, and then we're going to divide that by 9.8. It's going to read out as about 17.04 kilograms. In other words, this force of gravity is like maybe 20-ish% of what it was, and so the mass is going to be calculated out as about 20-ish% of what it should be. So that's kind of what's going on if you were standing on the moon versus the Earth. But then if you're in a moving elevator, it's going to depend a bit on how much acceleration you're feeling. So if you're staying on a scale, and you could actually do this in an elevator, it's relatively safe. You might get some weird looks from people, but you could bring a scale like made for Earth, go into an elevator, and read out how much you weigh. And if you accelerate upward, your stomach is going to kind of drop out a little bit. Or sorry, it's going to like drop when you end up falling. Like it's like, you lose that sense of like being normal because of that acceleration, and you get kind of compressed when you accelerate upward. And so you can feel that in that brief moment when you're being accelerating upward, you're going to have a readout on the scale that's like heavier than what it should be. So let's say that it's accelerating upward. In that moment, this force normal might be bigger than the force of gravity. So let's say the acceleration is positive. Then you've got unbalanced forces. So the sum of forces is going to be positive because that is related to the mass times the acceleration, meaning that force normal is bigger, like the magnitude of it is bigger than the force of gravity. Now, the force of gravity should be a negative number. The force normal should be a positive number. So that's how we're getting a positive sum of forces between the two. And therefore, as that force normal is being made bigger, you're going to be reading out on the scale a slightly higher value, because as the scale's having to push harder on you, you're actually pushing harder on the scale as well. So let's just say that I'm 100 kilograms. So like this force of gravity, it's constant. Let's say it's 980 newtons downward. But let's say that I'm accelerating to the point, it's a bit unrealistic, but let's say that it's like going twice as much as what I should be getting normally. So instead of 980, we're going to take 980 and times it by 2. So 980 times 2. Let's say that this value was 1,920 newtons. that's going to be reading out on the scale as like twice the value that it should be. So the scale's not going to say I'm 100 kilograms. It's going to say that I weigh 200 kilograms in a sense, like that readout from this. I don't actually weigh more. It's just the scale doesn't know that I'm accelerating. And so it's just going to feel that compression and give you a value. I like to think of this with the ones with springs. It makes more sense that the springs are being compressed a certain amount. Digital ones are a bit more complicated, but this same idea applies. So if we are thinking about this, maybe I'm in this situation, I am accelerating at a positive 9.8 meters per second squared. And I'm seeing that that's going to be like moving upward with the same acceleration because the sum of forces in this situation is a positive 980 newtons. So it's like I'm experiencing the same force as a net going upward than I would as if gravity was just pulling me down. So that acceleration of positive 9.8 meters per second squared corresponds with my 100 kilograms to help me understand what's going on with the sum of forces. Now, if you're accelerating at a slightly different value here than that 9.8, you just have to account for how the two forces come together and figure out what is going on with that normal force compared to the force of gravity to get you that sum of forces. And then plug that in into that formula of the mass times gravity and the acceleration that we're normally getting to figure out what it would read out. So that's the big picture on weight versus gravity. It is essentially how much gravity is pulling you down, but it is more accurate to talk about in terms of that normal force upward, because these two don't always equal each other. Like when the thing is accelerating upward, this value up and down, they're going to be a bit different. So we need to account for the fact that they are not exactly equal and opposite. And you can more easily do this elevator simulation than the one going to the moon, but the same principles apply as to why weight is different than mass. And in the context of your science class, we need to be talking about weight more in terms of these newtons.